Hi, I'm Chang Ming Wei, and my teammate is Wan Shakira, and we are going to discuss about the E1 lab, which is the half and full wave rectifier. The objective we are going to do this lab is to learn the half and full wave rectifier and learn the effect of the capacitor to the circuit. And these are the apparatus we are going to use in this lab. For part 1, we are going to do the half wave rectifier without capacitor. In this part, we are going to connect our circuit like this, and we are going to measure the input voltage and output voltage by using the oscilloscope. This is the data we get from the experiment, and in the table we can see that for channel 1 is the input voltage, and for the channel 2 is the output voltage. And we saw that the VPP and the VRMS of the channel 1 is higher than channel 2. This is because when you see the wavefront from the oscilloscope, you can see that the input voltage, which is the yellow one, is a perfect sine wave. But for the blue one is the output, we only saw the half of the sine wave. That means the negative part of the signal is being brought by this circuit. That's why the V peak to peak is only half of the input. So for the left hand side, you can see we are going to calculate the frequency, and we are compare the frequency for the input and output, and we are going to discuss this later on. For the part 2, we have done for the half wave rectifier with capacitor filter, and this part we do the same thing as the part 1, and we just add on the capacitor in this circuit. And the data we get in this part, we saw that for the higher capacitance, we have the lower V peak to peak, but the VRMS is just same. This can be explained by the diagram of the wavefront. For the 22 mF capacitance, we get the highest distance between the peak to the lowest part of the signal. For the blue one, you can see it. And we compare to the 44 mF, we saw that the distance from the peak to the bottom is smaller, and for the 100 mF is more smaller. So this shows that the VP peak for the higher capacitor will be lower. And we also calculate the time constant and the period and frequency in this part, and this will also be discussed later on. For the part 3, we are going to do the full wave rectifier without the capacitor. In this part, we have used the center tap full wave rectifier, and this is similar step as previous. And we saw that for the output, we have the double wavefront. It shows that the negative side of the wave from the input voltage is being reflected to the positive side, and therefore we have the double wavefront. However, for the V peak to peak, we also have the half for the output voltage compared to the input voltage because we only have the positive side. And for the full wave rectifier with capacitor filter, we just add on the capacitor, and this is the data we get. The data we get for this part is similar with the previous one, and however, we get some error for our 47 and 100 mF capacitance because theoretically the VP to peak for the 100 mF will be smaller than 47 mF, but in this lab we get higher for the 100 mF. And for the VRS, actually for the 47 mF, we are going to get 16.3 volt, but due to some sources of error, we get only 8.26. So never mind, we are also can use our data to explain the effect of the capacitor for full wave rectifier. This is similar for the part 2, that when we are adding our capacitance of the capacitor, we will get more smooth wavefront, and therefore the V peak to peak will be smaller. And this one is the part of the task and question. For the task 1, previously we have calculated the frequency of the signal for the input and output signal, and the formula we use is this F equal to 1 over T, and the percentage of difference for the frequency is calculated by using F out minus F in divided by F in times 100%. And this is the data we get. So from the table, we can saw that for the half wave rectifier, we get 0% of difference for the input and output. This is because for the half wave rectifier, it just broke the negative side. And for the full wave rectifier, we can double because for the full wave rectifier, it reflects the negative signal from the input side to the positive side, so it will get double wavefront. Therefore, the frequency will be double up. And in task 2, we have calculated the time constant by using this formula, and we are going to discuss the effect of the capacitor to the rectifier. From the calculation, we know that for the higher capacitor, we have the higher time constant, and we can explain the discharging process by using the formula, which is when our time constant is increased, the time needed for the discharge process is increased. So we will get the smoother wavefront when we increase our time constant. For the task 3, we are going to calculate the VDC for the half and full wave rectifier, and these are the formula we use. For the half wave rectifier, we get the VDC is smaller than the full wave rectifier. This is because for the full wave rectifier, we have double wavefront. Therefore, it will increase the VDC of the signal. And this is my part, and my teammate will going to discuss the other things.
Task 4. The question is, explain the difference of the LED brightness obtained in part 1 and part 3 in terms of power factor. From reference 2, we observe that the formula for calculate the theoretical power factor is V average square over VRMS square. From the experiment, the LED brightness that obtained in part 1 is greater than in part 3. From the formula that I showed the slide before, we can find the power factor for the half wave rectifier is 0.41. However, for full wave rectifier is 0.81. Therefore, the brightness of the LED of full wave rectifier will be greater. Task 5. The question is, give 3 common applications of rectifier in daily life. First, power supply for electronic devices such as laptop, mobile chargers, and other electronic that require DC voltage. Second, battery charging. Devices like car battery, charge, and power banks use rectifier to convert AC from the main to DC. Third, home appliances. For example, like television, refrigerator. Task 6. The question is, why is it important to filter the DC output from rectifier circuit? First, reduction of ripples. Capacitors move the output by filtering ripples in the rectifier DC signal. This creates a stable and smooth DC output, preventing voltage fluctuation that could disturb sensitive electronic components. Second, prevention of interference. Elevated DC can cause electromagnetic interference, disrupting the circuit. By filtering the output, capacitor minimizes noise, improving performance and reducing interference in other electronics. Okay, now we move to discussion. For the part 1, the data show the VRMS and VPP value in channel 2 are nearly half of those in channel 1. This occurs because the diode in the half-wave rectifier setup allows current to pass in only one direction, reducing the VRMS and VPP significantly at the output compared to the input. For part 2, the smoothness of the waveform improves as capacitance increases. This happens because the discharging time of the capacitor is proportional to capacitance. As the capacitance increases, the DC VRMS release and approach the peak voltage calculated as V equal 18.8 from part 1. At the same time, VPP decreased with higher capacitance. At the same time, VPP decreased with higher capacitance. This is because the capacitor charged to the peak voltage during the conduction peaks and discharges gradually during the non-conduction peaks. By reducing ripple voltage, the VPP becomes equivalent to the ripple voltage. Calculate using the formula. The formula is V ripples equal to I load over FC. However, the LED brightness observed in part 2 is more stable, brighter than in part 1. The reason is capacitor in part 2 contribute current to the circuit when the opposite direction of current locked by diode. In part 3, the VRMS in channel 2 is close to channel 1 because the full wave rectifier has converted 2 direction of AC current to the 1 direction. However, the VPP output still almost half of the input because the current now is only flow in 1 direction with the same VPP with input. The brightness of LED in this part is greater than part 1 because full wave rectifier can use 2 direction of AC current, but half wave rectifier can only use 1 direction of AC current. In part 4, the pattern of waveform is similar with the result in part 2, which is the smoothness of waveform can be right as 22 microfarad less than 47 microfarad less than 100 microfarad. The result is same with part 2. However, there is different VRMS result as part 2, which is the VRMS output more approach to VP input. However, there is a drop of VRMS for 47 microfarad. This may be caused by the some source of error that we discuss it later. Anyway, theoretically, the result should be similar with part 2. Apart from this, for the VPP is decreasing when the capacitance increase, which is the similar result with part 2. The reason of this result observed is also same with part 2. The source of error caused in unusual result in part 4 are the connection of the circuit may be loose. Besides that, the temperature of the apparatus increase after experiment being conducted for a long time will also could cause the apparatus cannot function well. Therefore, time gapping is needed for each part of experiment to reduce the error in this experiment. We move to conclusion. In this experiment, we learn how half-wave and full-wave rectifier work. The half-wave rectifier only uses one side of the AC signal, which makes the DC output uneven with a lot of ripples. The full-wave rectifier, however, uses both sides of the AC signal, so the DC output is much smoother. From this, we can see the full-wave rectifier are more effective and are better for providing. This is reference for our report.